we can estimate the number of tuples in relation S, which is the result of a selection with condition C on a relation R, as number of tuples in relation R divided by value count for attribute A of relation R that meets the condition C. We can estimate the size of a natural join of relations R and S with multiplication of number of tuples in each divided by maximum of value count for their shared tuples. Think about the why question for these estimations, and we will get back to it soon. Note that the estimation rules that we are discussing are not the only estimation rules you can apply. You can come up with your own estimation method, which can yield in more or less accurate estimation than these rules. We also have estimation rules for union, intersect, and difference. Union could be estimated as average of the sizes of two sets of tuples involved, or the size of the larger one. Intersect could be estimated as half of the smaller set of tuples involved. And difference of R minus S could be estimated with size of tuples in R minus half of size of tuples in S. Let's see these estimations in a simple example. Assume we have a relation R that has two attributes A and B. This relation has 10,000 tuples. We have another relation S, which is the result of selecting tuples that have attribute A equal to 10 or attribute B less than 20 in relation R. If the value count for attribute A of relation R, that is the number of distinct values relation R has in attribute A, is 50, and the number of tuples that satisfy B less than 20 is 1/3 of the total tuples, we want to find out what is the estimate for the size of S. Because value count for A is 50, this means it has 50 distinct values. So, by dividing 10,000 by 50, we have an estimation of 200 tuples with value A equals 10. The number of tuples that satisfy B less than 20 is 1/3 of the 10,000, which is 3,333. We can then estimate the final value to be sum of these two values in the simplest method, which will be 3,533. We can also use average of the sum and the size of the larger value, which is 3,333 plus 3,533 divided by 2. It's our choice. It's an estimate. Or another estimation that might consider properties of our attributes might be used. For example, if we are given the information that we have complete independence of attributes, we can use this last estimate, which uses the product of independent probabilities times the number of tuples. Using these simple estimations, we can then proceed to enumerating physical plans. The baseline approach is exhaustive and considers all combination of choices in cost-based enumeration. Each possible physical plan is assigned an estimated cost, and the one with the smallest cost is selected. However, there are other approaches within two broad class of approaches in exploring the space of possible physical plans: top-down and bottom-up. In top-down approach, we work down the tree of the logical query plan from the root. For each possible implementation of the operation at the root, each possible way to evaluate its arguments is considered, and the cost of each combination is computed. We take the best. In the bottom-up approach, for each sub-expression of the logical plan tree, the costs of all possible ways to compute that sub-expression are computed. Combining them in all possible ways, with implementations for the root operator, we arrive at the cost. Both of these approaches, though, consider all possible combinations. However, bottom-up approach based on dynamic programming has a more simplified method. We will discuss the details of these approaches and heuristic selection, branch and bound plan enumeration, hill climbing, and dynamic programming in our query optimization discussions shortly.